brain of the computer is going to request, it's always request for information. This as that you start the program on your system, on your computer, and also there is instructions of the program that is part of the computer stored inside the memory. So and then for your microprocessor to execute the instructions, it needs to request for those instructions from the memory. So that's why that's the main purpose of microprocessor to execute instructions. So now this line here is address line. This is an address line. So the CPU communicates for the memory using address line. So it uses this as address line to point to a particular location here to request for the instructions. And once it requests for instruction, the memory has to give it back. And so the memory was going to give back to the CPU using the data line. So these are the two lines that are very important in a microprocessor. So the CPU request for, let me put here, the CPU request for instructions of how to execute a code, or it can also request for a data from the memory. So then the memory will give it back using the data line, and they can actually use this line also to communicate also back and forth like that. So now that will now leads us to 8086. So 8086 microprocessor, it has 20 address line. It's 8086. So it has 20 address lines. So that means for this microprocessor to communicate to request for instruction, it needs a 20-bit address, 20-bit address to request for instructions. And then 8086 also has 16-bit. Sorry, I should put bit here. Sorry about that. So it has 16-bit data line, data address line, or data line address. I'm sorry about that. It shouldn't be address, it should just be address and data. Yeah, address and data. Sorry about that. So we have 16-bit here data line. So it uses that data line to what? To get the instruction which was requested for, and also communicate back also using the address line. So now, let me just actually cite the kind of advantage of 8086. You know, I said a box here is 80 bits, and then the data line of 8086 is 16 bits. So that means this 8086 can actually access two memory location at a time, which is actually which makes it more faster than previous ITEL microprocessors. I think with that, so the next thing is that we move to this. I was actually wanted to talk about the importance of 8086. I've just mentioned it. It has 20 bits address line, it has 16-bit data line, which is used to communicate, and also now in 8086, the segment address, which we are going to talk about now, don't worry. So the segment memory of 8086 is actually 16 bits. The segment memories are 16 bits. Now, for clarification, let me assume that we also call something. Let me start from here. So from here we go to memory segmentation. So physical memory, we can always hear this one. This kind of term every time. The physical memory. So what is physical memory? Physical memory is our RAM. We all know RAM. Yeah, it's our RAM. So when we load a program on our computer, the information, the instructions and data will be stored inside this RAM. So, and then this RAM is actually easier to access by the CPU. So the memory we are talking about here is also the RAM, and it's called physical memory. So, and then this memory is actually kind of it has no segments yet. Now to make this CPU to be able to access this memory faster and easier, that's where we now come to memory segmentation. So what's meaning of memory segmentation is like segmenting our memory in kind of certain areas like that. Yeah, instead of what I want to say, I don't know how to put that, but we all know actually what we call segments. Let me just put it here so that I'm not going to rub this one up. So it's like just creating segments like that, like having a stack like that. So like this is a segment, this is a segment, this is a segment. So each are what? Each are segments. So we have segment 1, we have segment 2, we have segment 3, and so on and so forth. Now, our physical memory, which is this physical memory. So these are physical memory. So it's actually segmented into 16-bit segments. So into 16 logical segments. So our physical memory is segmented into what? 16 logical segments. And this out of these 16 logical segments, so this 16 logical from here down to here, this 16 logical segment is 1 megabyte. So it's actually 1 megabyte, which makes that each segment is, so each segment is 64 kilobytes. So if each segment here is 64, 64, 64, 64, so 64 is per 16, that will give us 1 megabyte. So out of this 1 megabyte, or out of the segments that we have here, which is up to 16, so let me just say so let's say this is 1, so up to 16. So out of these 16 segments, our 8086, let me put this here. So our 8086 microprocessor can only access 4 segment memory. So out of these 16 segments, our 8086 can only access 4 segment memories. So what are the 4 segment memory that we have? We have the code segment. We have the stack segment. We have the data segment, and we have the extra segment. So these are the 4 segments out of this physical memory that our 8086 can access. So now let's try and explain these code segments, stack segments, data segments, and extra segments. So before we go, so I'll try and draw my physical memory again, which is my RAM. So I'll just draw some segments. 1. So between each segment, there should be a paragraph. Between each segment. So a paragraph is, let me show this one here. Okay, so a paragraph is just a distance from one segment to another segment. That's a paragraph. Distance, let's call this one our code segments. Okay, now about paragraph we are going to talk about in the next video, so try and subscribe to local heads, right? So let's come back again. So we have the first one, we have the code segment. So the second one, we have the stack segment. And here there should be another paragraph whereby we're going to have our data segment. We have another paragraph. Then we have our extra. Sorry about my writing. Extra segment. So we still have more down here, but the ones our 8086 can access is just this, and this. So the other memory up here cannot be accessed by 8086. The other memory down here, which is the bottom, cannot be accessed by 8086. So let's start. So what is code segment? So the code segment, all right, so code segment. So code segment is actually, it stores the instructions of a program. It stores instructions. So that's it. So what is instruction? Instruction is just a line of code that you write for a microprocessor to be executed like that.
More in the next video.
Okay, so we'll talk about that more in the next video. So it stores what? Instructions. So then we move to the next one, which is the stack segment. So for the stack segment, it is used to store, it stores return addresses. So these return addresses actually, we just need to understand that, but okay, right. So let me just give you an example so that we just understand it. So we'll talk about that in the next video, more about that in the next video. So what's a returning address? A returning address, example, let's say I write a program that has the main function. Let's say the main function, here is the main function. And inside this main function, actually let's say I call another function, which is like, let's say call setup function. Now let me declare let's say I have my setup here, my setup function here. So the meaning of return address is that when the microprocessor starts, we have a kind of code here and that code below it. So when it gets to this call, the microprocessor is going to store the address of this particular point. We talk about that in more next video. We have this kind of IP, which is a EIP, which is the instruction pointer. Actually, it points to this kind of line. We have number 1, number 2. So that the same way our microprocessor works. So it takes it line by line. So when it gets to this line, it's going to store the address of this line here inside the stack segment, in case, so that it's not going to actually, if you not store this one and it comes back here, so when it comes back to the main, it won't know where to start again. So it's going to store the address of this particular position inside the stack segment. So then it's going to come to the setup. So after executing all the codes inside this setup, it won't come back directly here. It will go inside the stack segment to look for the address where it actually made a call or made a jump to another function. So it's going to retrieve that address from the stack segment. Then now continue to what? It continues to execute the other following code. I think we are good with that. So the next one is the data segment. So the data segment is just very simple. It just stores the data. If you are writing a program, you actually have a data, like let A equals to this, let's say equals to that. So it stores data of the program. And also this extra segment can be used by the programmer or the coder, or can be used by you anytime. It's actually very free. That's why you call it extras. Like you have extra memory to use. You can just use it to do anything. You can use it to do a kind of arithmetic operation, anything you want to use it to do. So it's very free. But the major thing that you can use it to do is just to store data, like also, it also stores data, very simple like that. So these are the what? These are the 4 segments that we have that the 86 can access in our, let me write here, in our physical memory. So this is it. So then, and then there's one thing we need to know also. I said these our 8086, our microprocessor, to communicate with the memory, it needs 20-bit address line. And I said earlier here, I said that each segment is actually each segment is 64, right? And it's also 16-bit. So that means each segment is what? Is a 16-bit and it's 64 kilobytes. So that means a segment here is 64, 64, 64, 64, 64, 64, and they also what? 16-bit segment memory. So how can 16-bit segment memory access a 20-bit memory inside our physical memory? And that is why the processor itself actually emulates what we call what? Appending zeros. Okay, appending 0h. So what's the meaning of appending 0h? So inside this segment, inside the 4 segment that we have here, so it's 16-bit. 16-bit has to be, if I want to represent it in hexadecimal, 16-bit has to be like let's say F, 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 and F, H. So and each F is what? Each F. Let me put it here. Each hexadecimal, that hexadecimal digits is a 4-bit. So that means 4 bits, 4 bits, 4 bits. 4 times 4. That makes it what? 16 bits. And we need to make each segment 20 bits. So that's why we're going to add a 0 to what? To our, what's it called? Our segment memory. So that will now be, so each segment memory is now what? It's going to be let's say code segment memory. So the memory that you plus what? That will be additional of what? Of 0h. So let's make an example here, then we call it a day like that. So okay, so let's say I have a memory a segment memory of like let's say f ff0, let's say 02h. This is my memory. This one is the memory segment. Sorry. All right. Okay, now so that's not this is a memory location. This is a memory location. This one could be a memory location inside the code, data, blah blah blah, all these 4 segments. So let's say this is a memory location inside the code segment for an example. So now append 0. It's going to take like ff0 2 then 0h. So this will be by what? So that's 1 2 3 4 5. And each hexadecimal is a what? Is a 4-bit. So that will now be 4 times 5. Makes it a 20-bit like that. So the microprocessor will now use this memory location plus offset. We are going to talk about that in the next video. So a memory location or a segment, let me just give you the formula. So the segment, so we'll talk about that in this lecture. So segment plus offset, we'll talk about offset, equals to physical memory location. So it uses this one plus the offset, and the offset is 16 bits, and this one is 20 bits. If we add this one and this one together, we are still going to have 16 bits like that. So sorry, 20 bits. So it uses this guy here to know where the particular instruction or the particular data is inside our physical memory, which actually comes back to this. So just take that 20 bits, then it points to the target. So the target depends on the kind of value you have here. The kind of value this one is, the kind of value the offset is. It's going to plus them together by itself. Then it's going to point to the target area in the physical memory. Then you get then it's going to retrieve the instruction or data. Then it actually takes that process every time, continuously like that. So that will be the end of this video. All right, thank you for watching this video. In the next class, we are going to talk about addressing mode, paragraph, and offset. And if you have any questions, you can drop it in the comments below. Thank you guys for watching. If you want more breakdowns of your class lectures and down to earth explanations, subscribe to Local Earth right away and share this video with friends you do love and enemies you do love play with.
Champion. Yeah. Said them vipers. Kill them with the kindness, love build snipers. Sing a sweeter melody than Peter Piper. Have them ducking corners, now we have a crisis. Heart on my sleeve, flowing the nicest. Never miss a beat, no, I know where the mic is. Renegade blood bleeds red the brightest. SSG general, I rule, I'm timeless. Born again, looking up to heaven.